So good day, we are the group 10 and we will be presenting our pulse time modulation signal generator circuit. So for the basic operation of this circuit produces both PWM and PPM signals from an input sine wave signal. So this circuit contains two 555 ICs that will serve as a astable multivibrator and a monostable multivibrator. So the PWM signal will be obtained from the astable multivibrator, while the PPM will be the output of the monostable multivibrator.
A vibrator circuit is this one. The timer continuously changes its output high to low and vice versa. If a variable voltage is applied at control input pin number 5 of IC555 or A1, it's a stable mode, then the width of the output pulse will change accordingly. The values of R1, R2, and C1 are chosen to generate pulse train signals. The width of the OP pulse will change in accordance with the amplitude of the audio signal. The input signal is applied to a stable stage and its output is the input of the monostable stage, which at its output gives us a pulse position modulated signal or PPM signal. The input signal is applied to the control terminal of a stable multivibrator when the input signal amplitude varies the control terminal. The voltage changes and the switching voltage of a stable multivibrator changes accordingly, and the width of the output pulse of the stable multivibrator changes.
So the PWM output from the stable multivibrator will be used as the input of this monostable multivibrator. Then the output of this monostable multivibrator will be in the form of PPM signal. This circuit diagram shows how a 555 timer IC is configured to function as a basic monostable multivibrator. A monostable multivibrator is a timing circuit that changes state once triggered, but returns to its original state after a certain time delay. It got its name from the fact that only one of its output states is stable. It is also known as a one-shot. In this circuit, a negative pulse applied at pin 2 triggers an internal flip-flop that turns off pin 7's discharge transistor, allowing C1 to charge up through R1. At the same time, the flip-flop brings the output pin 3 level to high. When capacitor C1 is charged up to about 2/3 of VCC, the flip-flop is triggered once again, this time making the pin 3 output low, and turning on pin 7's discharge transistor, which discharge C1 to ground. This circuit, in effect, produces a pulse at pin 3 whose width T is just the product of R1 and C1. For example, T is equals to R1, C1.
I will be running now the circuit. And as you can see, at the right side, this is the output of the circuit. The first one is the blue one, which is the modulated signal. The second one is the green one, which is the pulse width modulation, or what you call PWM signal. And the third one is the pulse position modulation, or what you call the PPM signal.
For the description of each waveform, a factor that generates a key difference between PWM and PPM is that in PWM width of the pulses shows that proportionality with the amplitude of message signal, whereas in PPM, the position of the pulses is proportional to the amplitude of analog modulating signal. It is to be noted here that the position of the pulses changes according to the reference pulses. Basically, the falling edge of PWM pulses acts as the starting of PPM pulses.